All right, so this is what's happening out there right now. So I'm going to drive the bus, but oh, and also what you're looking at, sorry, you probably, what are we looking at a bunch of spaghetti here. We're looking at a bunch of different things. We're looking at precipitation. That's all of the red and the blue. Obviously the the green is rain, blue is snow, right? Okay, got that established. So this blue line here that you see, this is what's called the 540 line, okay? Now, we'll learn about what that is. 540 line is basically, I'll get that. The 540 line is basically the freezing line, so to speak, okay? So this is the line where the cold air kind of takes over. Now, does that always mean that it's going to be snow just north of that? Not necessarily, but it means it's going to be pretty darn cold. So that's the line we watch for where the cold air really starts to intrude. So as I tick through the different hours in this forecast model, this is this morning, by the way, watch where that line goes, because that's going to be important. So what we've got going on right here is we have a jet stream. Remember, the jet stream is the one way up high. It's the one that the jets fly in. It's about 30 to 40,000 feet, okay? And this is kind of the bus that drives all the weather closer to the surface. So the jet stream right now is doing this, okay? So notice we got a bit of a dip right in the Midwest, right? Right up here in the Great Lakes. Coincidentally, that's where our little cold line is, our blue line, our 540 line. So we are under the influence of some fairly warmer air. Now watch what happens over the next couple of days as we click on through. You can click through, you can just watch. Totally your choice. So there's this afternoon. Now notice what we're seeing. Two different things that we have on the map here. Here's our area of high pressure. This is what's kept us sunny with 0 clouds over the weekend, right? So we can thank this for this beautiful weekend we just had. That's starting to slide off to the east. What direction do the winds go around the high? Clockwise or counterclockwise?
Clockwise.
Right, clockwise. So if winds are going clockwise, look what's happening. So we're starting to feed in all this moisture, right? Starting to put it back into the sky. What you're going to notice this afternoon, we're going to see a little more cloud cover. It's going to be real thin stuff, but it'll be out by tomorrow. It'll be back to those puffy clouds. And you go, something's happening, right? Because we're starting to pump more moisture in the atmosphere. Now notice that the same thing we talked about at the very beginning of the class. If we've got high pressure here, and that's moving away, we can't have a vacuum, right? We can't have an absence of space. So if high pressure moves away, what's probably going to move in its place? Oh, looky there. There's a little low pressure starting to develop, okay? Watch that guy, because that's going to be important. So this is tomorrow morning. There's tomorrow evening. And look what's starting to form. What's that look like? Looks like cold front, doesn't it? Mm-hmm. Right? So same story. We've got, here's our high. So it's driving all of this moisture in, okay? The low is way up here. And so we've got a front. It starts here, and it goes all the way down, okay? And I left my blue marker here, and somebody took it. I didn't realize these things were this valuable.
But it has different colors, like it has the red and then the blue. Does it mean that it's also a low and a high in a specific area, or does it mean?
No, not necessarily. You mean like right here?
No. On the line, you know how like usually when they're doing a forecast, they have the line and they have like the red and then the.
Oh, I see what you're saying. Yeah. So generally, what that is, so what the way this would look. Imagine that's blue, because it's cold front, is there will be a warm front right here. And it'll look like that. So that would generally be red, because that'd be the warmer air moving out ahead. And this would be blue, and this would be cold, because you've got all of the cold air. We'll use Halloween colors. You have all the cold air moving down like this, okay? So that's the setup. We've got warm air that's doing this, and we've got cold air slamming through, okay? So we've got two air masses that are clashing with each other, and we're going to get caught in the middle of that, all right? So that's about 12 o'clock Wednesday afternoon, okay? So notice scattered showers, thunderstorms probably starting to develop. Here's the interesting thing, too. This is what we're going to talk about today. We're going to talk about what's happening at the upper part of the atmosphere and at the surface. At the surface, the area of low pressure is right here, okay? In the higher part of the atmosphere, what we call the upper air analysis, the low is right there. That's kind of weird, isn't it? Why wouldn't it be here? Well, the easiest way to explain this, the way somebody taught me years ago, was if you're pushing a baby stroller, right? Because all of you have kids out here, right? Yeah, and everybody's like, oh. Anyway, if you're pushing a baby stroller, the fulcrum, or the part that's doing the work, is you, right? And you're up here. Baby and the stroller are down there. So now it can go by itself, but in order for it to move, it has to have some kind of force behind it, right? So you're pushing it like this, and you're making everything in front of the stroller move. Part of the stroller itself is moving. So the upper air low, the upper air dynamics work the same way. Even though the cold air is moving in, here's the jet stream, okay? So the cold air is pushing south, the warm air is getting pushed north, but what's eventually moving and kicking this whole thing through is this upper level low right here. So this is kind of the top part of the baby carriage pushing down. The way to think about this, and this is going to be a little tough, and it'll make more sense because we're going to start talking in 3D terms. Think of it in terms of 3 dimensions, meaning that at the surface is down here, and what's happening above the surface is up here. So the whole thing is driving like this. Okay? So that's how sometimes surface lows and upper lows can get out of phase with each other. Is because one is behind the other, but it's driving the whole thing through. Okay? Like I said, this will make a little more sense in a bit. But keep your eye on that. And what happens with this as we get into the afternoon. Okay? So that's 12 o'clock. There's 6 p.m. Notice as we go from 12 to 6, colors get a lot brighter, don't they? Things get a little more aggressive. Okay? That's why we think that we've got a potential we could see some strong storms running through here. And there's midnight. So what have we done? There's our low. There it is. And now we've got another little surface low that's developed. And notice that the main low is way up here in Canada, so it's kind of cut itself off. So there's Thursday morning, Thursday afternoon. Now, by the way, I think that we're looking at a real good severe weather outbreak across the southeast by Thursday. This could be an interesting one. A lot of the weather guys across the southeast are all starting to put up some red flags that things could get a little ugly. All right, so now notice, let me show. So there's Wednesday night and Thursday morning. So all of this moves on through. So what we've created with this is a scenario where there's our cold line. So we have all this cold air plunging southward like this. All right? Now, what you get sometimes in the jet stream is you can get these real fast moving, it's called an exit region. And it's kind of like the same way that air moves through a jet engine. It gets pulled in through the jet engine and it shoots out the back, okay? So the way this air is moving in the jet stream, and we'll create a little tube for it here, is like this, okay? So when you get to, if you can visualize it, visualize this air moving south, gets to the bottom of the curve, and what happens? What happens when you're on a roller coaster and you get down to the bottom? Where would the momentum take you? Right, it'd go back up, wouldn't it? Right? You would just sit at the bottom because you've built up all this speed as you get down to the bottom of that roller coaster. When you get to the bottom, you shoot through, right? You just fire through like that. It's a slingshot effect. So what happens sometimes is in these jet streams, you can get this little area where the air is being forced through there so quickly it creates more lift. Okay, that's what we call a jet stream. And that's sometimes where the computer models will pick up on the potential for some real heavy rain and severe weather, because it sees that the air is firing through and it's moving into a more favorable environment. So I think there's a good potential that we could see some nasty stuff coming through here Wednesday afternoon, which just means longer day for me. It's okay. I'm going to show you one other thing. You don't have to jump here. You can just watch up top. Let's go. I want to show you an upper air model, just so you get an idea of what we're looking at. So anyway, so the cool thing is that by the time we get to Wednesday morning's class, we should have a really good handle on the timing when this has come through, and then we'll be able to kind of watch it, and we can track it Wednesday morning too. Okay, so here's this morning. So what you're looking at here, this is the 500 level of the atmosphere. So this is kind of the jet stream where things roll. The cool thing about looking at upper air analysis like this is it's really easy to spot where the highs and the lows are, right? Low, high. Right? If the lines are being forced up, you've got an area of high pressure building. If the lines are being forced down, you've got an area of low pressure. And if you move through back and forth, if you toggle the little scrubber up there, you'll see this going counterclockwise. There you go. There's our low. Okay? So watch. There's Wednesday or Tuesday afternoon. And then as we get into Wednesday, what are we seeing? Remember we looked at easy. Okay, so there's Wednesday evening. You've got a nice little dip right here, right? Okay, if we look at that, here above. There. Okay, and then we go back to our forecast model. There's the exact same time. See that same dip, right? Dip's right there. Let's go here. Pretty much in the same place. That's good. So that's what we were looking at. We're tracking the upper level low that's moving all this through. Now what happens sometimes is when you get these big dips in the jet stream, just east of there or just out ahead of that is where you can get the strongest push and uplift of all of the air. And just so happens that that's the case by, late Wednesday evening. That's right across East and Southeast Texas. That's why we think we've got a potential, could see some strong storms as that pushes through. So once that does, see it kind of fire on through, and then here's where things could get a little ugly. It's the same scenario. You've got nice big dip through here. You have all this warm air getting shot out ahead of that, and this is likely going to be our big trigger spot for Thursday. And this is kind of the time when things happen like this, and so what you'll get is you'll get these big dips. Here comes another one. Friday into Saturday, which is not going to be our problem, thankfully. But it's the same story. So you have all of this cold air plunging south down into the jet stream. So meaning that once we get this front through, Friday, Saturday, Sunday are going to be really fall-like. We're talking probably mid-60s for highs, maybe even cooler, 40s at night. So it'll be some nice weather. But this is the time period in fall when things start to get a little more active as they work their way through. So this is what the upper air analysis looks like versus what's happening at the surface. So once that's through, there's what? Thursday. There comes the second one. So notice, right, this one doesn't look as aggressive. We're not seeing as bright of colors like over here. And partly because this doesn't have anything at the surface attached to it. This is just kind of an upper low that's driving through. But what's happening is all of this cold air up here in Canada and central Canada, that's all being pushed down right across the state of Texas like this. Which is why by Friday, Saturday, and into Sunday, we're going to see pretty darn cool forecasts. In fact, if we look at said forecast, let's go. Just do it from the top up. Show you. Oh, we got our hooks. Woo! Half mile visibility. So showers and thunderstorms. Then look as we get into Thursday, Friday, and Saturday. 67, 70, mid-40s. So really nice forecast. We just got to get through Wednesday, and we'll be okay. So we'll watch this as we head in towards Wednesday's forecast as well. This will be some very interesting stuff. All right. Now that I've bored you all with that. Love it. Okay. Let's talk about wind. So wind's actually pretty easy. Sort of. Wind is basically just a movement of an air mass, and it's created by some type of acceleration. Okay? Now, forces that are acting on the wind can be all kinds of things. It can be a gradient, which is a difference in something, which can be a difference in temperature. It can be a difference in air mass. It can be a front, something that's pushing the air through. But there has to be some kind of difference. Gravity, friction. You know, why does it get breezy when you go out on the third floor and head out towards the light rail stop? Anybody ever notice that whenever you stand outside there? Like the wind seems to really pick up through that, you know, if you don't go out where the light rail stop is there, over by the bookstore, but if you're just standing outside underneath the brick part of why is that? What do you think? Why is it always windy through there?
Because of the cars and the wind that they create.
Yeah, right. Cars moving through, light rail, and the fact that just the wind as it's going up over the bridge, it's not an open space. You're forcing it through a little tunnel. And so whenever you get in there, that tunnel gets really, really going. And so that's kind of what happens with wind. It's that tunnel itself is helping to create wind as it moves. So the idea here is that you've got a local motion of air relative to the Earth's surface, some kind of force that's pushing or pulling on that. And that force acts on the wind. So as we said, that could be an air pressure gradient, the difference between a high and a low. Okay? That could be forcing some of the air through. Centripetal force, which already figures, you know, some of the spinning of the Earth's atmosphere itself, that can cause wind. Coriolis effect, curvature of it, friction and gravity. So pressure gradient force, and this is the one that we're going to learn most about because this is basically what creates most, if not all, wind at the surface. All right? So this is a horizontal change along a surface. All right? So what I mean by that is that one air mass is pushing another air mass out of the way. And so what you're doing here is you're creating some kind of a pressure change. All right? Now how we track that in terms of weather is done on a horizontal gradient. Whenever I say the word gradient, I mean a difference, a change in one mass, one place or the other. That's what we're talking about when we talk about a gradient. Okay? So the way we look at it on weather maps is we look for changes in this guy right here, this word. Okay? An isobar. An isobar is a measure of constant pressure. Okay? This is how airplanes stay in the sky, sort of. Or when they're flying in the sky, this is how airplanes don't bounce around everywhere. It's because the computers in the airplanes lock into a certain pressure reading, a line of pressure, and that's what they follow. One of the reasons why it's always a little bumpy, not always, but most times it's a little bumpy when you're taking off than when you're landing. Because what you're doing is you're crossing the isobars. So you're moving through different pressure levels of the atmosphere. We already know that the atmosphere, the pressure is greater near the surface, right? And then it gets less and less as we go up because we're getting away from what? What's the greatest force we have on this planet? Gravity, right. We're getting away from gravity. And so as we get higher up into the sky, the pressure levels and readings get more and more stable, which is why, you know, airplanes now figure the best way to fly is at the jet stream level, about 30,000 feet up, because it's relatively light up there. There's not a lot of pressure changes. Things are relatively stable. Okay? So what we look for is we try to find these isobar patterns. The way we look on our weather maps is they are all drawn at 4 MB. MB stands for millibar. So we're going to use that term for the rest of the course here when we talk about millibars. Millibar is basically just a pressure reading. Okay? So the way these look is just like this. I'll show you. Let's go back to our map. Okay. So if we look on these, all of these little squiggly lines represent different isobars. Okay? So the way to track these is they're numbered. Now, they're numbered here in particular because we're looking at a thickness map, which I'll explain what that is in a bit. So this is 528, and the numbers don't mean anything to you right now. Don't worry about that. We'll get into that. Just kind of understand the concept. 528, 534, 540, 546, 552, 558, 564, 570. Okay? So notice as we get lower, as we go down in latitude, the numbers get higher and higher. Okay? So easy rule of thumb is the lower the number, the colder the air mass. Okay? So that's why we say we always track this sort of 540 line, and that's why the 540 versus the 546, one is blue, one is red. So this generally means colder air, generally means warmer air the higher that number gets. Okay? So if we were to go to the surface map, like that, that'll make a little more sense here.
And you said can you say that last part again where you said like the rule of thumb is?
Oh yeah, rule of thumb is that the lower the number, the colder the air. Yeah. Surface map. Let's go. Hold on here. I want a surface map. Okay. That's good. There we go. Okay. Okay, that should do it. So what we're looking at here is a surface map, and we've got all of our surface observations in terms of our air pressure levels. Okay? So 1028, 1024, 1020, 1016, 1014. So what you're seeing is the higher the number, the closer it is to the center of high pressure. Now, as the numbers go down, there's 1024, 1020, 1016, 1014. What have we found? Oh, looky, an area of low pressure, right? So even if I didn't have the H's and the L's on this map, you could find where those areas of high and low pressure are based on what the numbers are that you're reading on the isobars. Okay? Same thing here. 1024, this is probably what? There's the 1020, 16, 12, 8, all the way down to probably a 998 or something like that. So there's our area of low pressure. So now the way this works in terms of wind is everything flows from high to low, okay? Just like when we turn with temperature. The higher the temperature it is, it tries to go to the lower temperature and balance things out. So the air pressure works the same way. Too much high pressure, too low pressure somewhere, the high is going to go to the low. How that happens is it creates this. This, where the lines get all kind of packed in here real tight. See how they're a little more spread out as they get closer to the high, and then as it gets to the low, it gets like tighter and tighter and tighter. So what's happening is we're creating a gradient, okay? And that gradient is basically just a difference in something. In this case, it's a difference in pressure. So what we're doing is as we get this gradient tighter and tighter, wind is going, remember it's going clockwise, wind is going like this. Okay? It's going from high to low. So the wind is actually working towards that area of low pressure. So if we were to look at this scenario, there'd be two different things going on in the northwest. We'd have wind being pushed in by this area of high pressure, and then we'd have wind being pulled in by this area of low pressure. Okay? So thus, the more that gets pulled into this, and we already know about areas of low pressure, if we pull the air into the surface, what's going to happen? It's going to rise, right? It's going to start to create these big storms. And that's what we're seeing. So that gradient is moving that wind closer and closer to the coastline there. So that's sort of a one scenario that's created that moves wind itself. Okay. So basically it's measured in the direction of the greatest change, and it works perpendicular to those isobars. Okay? So just as I was saying, the closer these isobars are packed together, the stronger the gradient, the stronger the wind. It's the easiest way to remember that. So what you're going to see in this scenario, come on, you're going to see very strong, fast-moving wind. And in this scenario where they're a little more spread out, the winds will be a lot lighter. Okay? So anytime you look at a weather map, if you look at those isobars and you see where they're really packed in pretty tightly, the wind's going to be a lot stronger. So widely spaced isobars, it's a weaker pressure gradient. The air pressure changes is going to be a little more gradual versus really strong. Yes, sir?
Is that kind of like radio waves we were talking about earlier?
Mm-hmm.
Like an FM wave is going to be clearer, like a better.
Yeah, because it's got a higher
So-
frequency. Yeah, it's got a higher frequency. To a degree, I mean the wavelength it's more on wavelength size versus any spacing between those wavelengths. But yeah, the concept's sort of
Like
the
a
same
student
thing.
just to help.
Yeah,
know
uh-huh.
this.
Yeah, it's the same thing. So it's just like if you take water in a big pipe and you put it into a smaller pipe, what happens? You increase the velocity, right? So it's the same scenario. If you've got wider space between these isobars, the wind's going to travel through fairly easily. If you tighten up, pack that in, you're going to pick up speed. So, and if you look at our so here's the wind speed. So notice as we get to, ooh, we get a little jet streak. Telling you what, go see some business. Why not, right? It's a holiday. That's what happens around here on holidays. Things get crazy. So, but if you look at this, perfect example. You know, we've got high pressure here. Look how far spaced these are, right? Pretty wide open. Look as you get, there's our little upper low. Look what happens here. See how tightly packed they are? And the tighter they're packed, look what we have here. This little red area represents a jet streak, meaning, and these are wind barbs too, by the way. We'll learn about those in just about 5 minutes here. So these are showing wind speed. Each one of these little notches is 10 knots, okay? So that's 1, 2, 3, 4, about 4.5. So that's about 45, 50 knots. As you get in here, when it starts getting black, that starts at 50. So 50 looks like 75, 80 knots, right? So we could be talking close to 100-mile-an-hour winds. Now, at the surface, that'd be a hurricane, right? That's not the case. That's in the upper part of the atmosphere. But as we said, go back to the buggy idea. If I've got a 100-mile-an-hour wind up here, how fast can I push that buggy at the surface, right? I can really fire things through. And so that's why that bullseye for the biggest potential for thunderstorm explosion will likely be right about in that same spot. Because if this wind is firing through, think back to your roller coaster idea. If your roller coaster is going down and it gets to the bottom of that hill, is it going to just kind of like stay there? No. What's the momentum going to do? If it goes down to the bottom of this hill, right, it's going to go boom and just fire right through. Okay? So the tighter those things are packed together, the fast. It's good English statement. The faster that'll create. So pressure gradient force, this is a great example too. I've always loved this one. Is the idea that you've got, if you're taking water in a tub and you're sloshing it back and forth, what you're doing is you're creating sort of an example of horizontal air pressure gradient, okay? So as you're pushing the water, as the water pushes away, you're creating more water being pushed in one direction. So that's increasing the pressure, right? And so it decreases the pressure where you're at. But if once that water comes back, what happens? Then you switch that. It starts to increase the pressure closer to you, decreases it where it is there. So that's kind of that horizontal gradient that you can create. And that's what the pressure does when those isobars pack in. So the idea with pressure gradient force, as it says, is that when it develops, the air flows in a direction to eliminate that gradient, right? That idea of balance. The Earth's trying to balance itself out. If the air is moving too fast, it's too packed in one direction and not enough in the other, it's going to move in that direction to try to balance everything out. Okay. Has everybody got that concept so far? Kind of how? Okay, good. That's important. Okay. Centrifugal force, Coriolis, which we already talked about Coriolis. Right? Remember, the Coriolis is the deflection of the wind itself because of the rotation of the Earth. So that, remember, we used the scenario that if you're in a bomber, you know, and you're trying to bomb, you're 30,000 feet up and you're going to drop a bomb on New York City, okay? Are you going to drop it directly over New York City? No, because you'll probably hit Detroit, right? Because the Earth is turning. As the Earth is turning around, you need to, if your target is here, you got to drop it now, because by the time it hits, it'll move. So that's the idea of the Coriolis effect. So what happens with that is there's deflection depending on where you are on the planet, okay? So in the northern hemisphere, which is where we are, the deflection is to the right. And so as the Earth turns, it'll start to deflect off to the right. And then same thing, just the opposite in the southern hemisphere, everything will deflect to the left. So the Coriolis effect doesn't have much of an effect on wind locally where we are, but more on a global scale. If we look at the global wind patterns as they kind of move through the atmosphere, that'll give us an indication that there's a little bit of deflection. But it's not, the pressure gradient force is the one that is pretty much going to rule what we're talking about. This is just one that I'll show you because it's out there. Okay. Another important one that can move everything through is friction. A couple of different ways this happens. Friction, just as a definition, is the resistance of an object as it moves in contact with another object or medium. I always love when they use the word medium. It always makes me think of that Long Island lady. You know, it's on TLC or whatever. So funny, my daughter last week goes, "Dad, do you know she talks to dead people?" Yeah. And I was like, "Yeah, she does." She's like, "I want to do that." I'm like, "No. I'll have her watch Ouija, and we'll figure out that's a bad idea." Or what's that movie, that lady that has the demon that follows her around? Paranormal Activity. That's it. You ever seen that one, the first one? That movie's crazy. Watch it. It's a good one. It's a really good one. The rest of them stink, but the first one's great. Anyway, okay, so viscosity. We all know what viscosity is. If you ever watch commercials about, oil, they always talk about the viscosity breakdown, blah, 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 right? What does it mean? Well, it's basically just talking about some kind of a friction of fluid, right? Gas, liquid, water, whatever. So water can create its own friction, which can change the type of flow that can move through it, right? Why do people do resistance training in water? Right, because it creates more resistance, And the best part is that, especially for athletes, or if you have like knee problems, ankle problems, things like that, a lot of times you'll do recovery training, resistance training in water because there's not the same gravitational impact if you're pounding on the ground here, right? You're still getting resistance, but it's a different type of resistance. Another interesting thing, if anybody ever been down to the Johnson Space Center at NASA and you've seen the tank that they use? Have you seen it? It's crazy, isn't it? So it's basically a huge freaking swimming pool, and it's a tank, and they take all of their equipment if they have stuff they're trying out or procedures, or even if they've got astronaut training, and they'll drop them in there. Anybody remember what was that crazy asteroid movie with Bruce Willis? What was that called?
Armageddon.
Yeah, like Armageddon. Remember when they go in there? And if you've seen that, that's how they actually train, because it mimics space to the best degree of anything that we've found so far. Because you're in water, there's not the effect of gravity where you're going to just immediately sink, right? And everything you do is going to be really slow, like out in space, because there's no air, there's no resistance to it. You have to kind of learn how to operate in a more viscosity latent atmosphere. So that's one way to do it. So a couple of different ways. Viscosity, it works on the molecular level. That's random motion of molecules in the fluid, yes. And then the eddy viscosity, which is what we're concerned with, not your cousin Eddie. This is Eddie with a Y. This is curvatures or swirls, movements within the fluid itself. And that's what we're going to be studying when we talk about the atmosphere. All of the little lows that move on through, those are like little vortices or little eddies that work their way through. Okay? And then the flow, characterized by this movement, this sort of viscosity, this friction, is called turbulence. It's the same thing that, like I said, when you go up in the sky in a plane or you go down and you're landing, you're running through all these little eddies. You're creating more viscosity as you're moving into the atmosphere. And so that's what creates that turbulence. So a couple of different ways that this looks like. These are great examples too. Snow fences. Snow fences are built to create friction, right? We don't see them here, obviously, because we don't have snow. But if you're out west, if you're out on the Front Range, Colorado, Nebraska, Wyoming, the Dakotas, if you're driving along the highway, you'll see these fences. They're not real big, but they're out there, and it's just right. Am I right? Right?
Yeah, it's right.
It's just miles and miles of them.
Yeah, when it's flat.
Yeah.
Otherwise, you can't drive.
Right.
On the highway.
Yeah, and they put them close to the highway because it serves as a bit of a friction barrier to all of the blowing snow that moves across. And so the snow will pile up against the fence, and then as the wind moves on through, sometimes it can create these really cool little snake-like patterns because that's the friction of the wind moving across that snow. Same thing if rocks in a stream bed. This is how rapids form. You know, if you've ever been down rapids or whitewater rafting or whatnot in Arkansas, places like that, and down in Big Bend, in Southwest Texas, that's what's being created. These little eddies are being created in the flow of the water itself. Snow rollers, same story. Okay, gravity. So so what we just learned there is horizontal friction, okay? Horizontal advection, movement of the air. Now gravity works to create vertical movement, right? Gravity is the biggest force we always know about. Gravity's going to pull everything down to the ground. But clearly that doesn't always happen because we get clouds. So clearly gravity ain't that good. It is, but there's just other forces that are working against that. Okay? So the idea here is that gravity is the net result, gravitation is centripetal force. Centripetal force is basically the idea that because the Earth is spinning, if you're spinning, and let's say you have a rock attached to, or a ball, not a rock, we'll go with a ball. If you have a ball attached to a string, okay, and you hold it out like this, and you stand there, what's it going to do? It's just going to hang there, right? But what if you start spinning around in a circle? Now, I'm not going to do that because I'll get really, really sick. I don't handle spinny things well. I don't. Like those teacups. You remember those teacups? You know those things where you, or what was it? The one thing you get in there and you spin, and you like spin it yourself. Oh my Lord. I'd be dead for hours. I just can't handle that stuff anymore. But if you take a rock on a string and you start to spin in a circle, what's going to happen to that rock? It's going to start to spread out, right? Exactly. And it's going to try to move away from you, because what you're creating is you're creating a centripetal force, okay? So the force of your motion is creating outward movement, because the rate of spin that you're creating is pushing things away from you. That's why, what is it, that one ride at the fair, you know, where you go in and they stand up and they kind of strap you down, and then you go spinning around, and the point, you know, you try to pull your hand out and it pulls back.
Yeah, like a long time ago.
That's gravitational
they didn't
force.
have seatbelts because.
Oh yeah, they didn't need them because you just get stuck to the side.
Right.
You know? Yeah, that's when we were all dumb and stupid. Ugh, that thing was gross too. Okay, yeah. Right, but the weaker centripetal force caused by the Earth's rotation, but gravity sort of works against that. So because the Earth is rotating, if centripetal force was the main factor that was governing us, we'd all be flying off the planet right now, right? Because we spin right off. But we don't, because gravity is too strong. So gravity pulls everything back. So it's always a push and pull between centripetal force and what's happening with gravity. Gravity wins out because it's the bigger of the two. Okay, so now we got the idea that we have a horizontal pressure gradient. That's responsible for initiating the air motion, getting things moving. We know that centripetal force creates that imbalance. Coriolis effect, we know, not real strong, but it's from the rotation of the Earth. Friction acts opposite of the wind direction, and then gravity pushes everything down to the ground. So we kind of have these concepts. So how does wind work in that? Glad you asked that. So a couple of different ways that wind works. Geostrophic and gradient wind. We're going to learn what both of those are. Both of those are governed by different forces in the sky. Okay? Very important. So here's how it works. So there's an idea called the hydrostatic equilibrium. And the idea of that is just what's the push and pull between the two main forces that we're dealing with in wind. All right? So the vertical pressure gradient force is always going to try to pull things up and away from the surface. Gravity is always going to try to pull things down. So we've got an imbalance. The question is, which one of these is going to win out? And that's what's going to determine what happens in terms of that air parcel. Okay? So, here's an easy way to remember it. As we increase our altitude, we decrease the air pressure, which we already know, right? Because the closer it is to the ground, the higher the amount of gravity's effect has on it. As we decrease altitude, as we go down from the sky, we increase the air pressure. It gets stronger and stronger and stronger, right? So the balance between these two forces is what's called the hydrostatic equilibrium. Meaning that any deviation we have in that, if there's either a stronger pressure gradient force or a stronger gravitational pull, that's going to that's going to cause these air parcels, our little bubbles of air, to accelerate vertically. Okay? So let's use this in a scenario. If I have, we'll go this. If I've got an area of low pressure, what do we know what's happening? Well, we know that wind is what? Moving in towards the center, And if we're overloading that center, where does it have to go?
Oh.
Right, it's going to go up. So in this scenario, vertical pressure gradient force wins out, right? Because if we're in an area of low pressure and we're creating clouds, thunderstorms, things like that, well, that has to win out. Because if gravity was the stronger of the two in that scenario, that area of low pressure wouldn't create anything, right? We wouldn't get any cloud cover. We wouldn't get anything to build. Yeah, nothing. All right? So let's flip that. And if we have an area of high pressure, we already know that the air moves away from the area of high pressure. So if we're creating an absence here, what do we got to do? We got to pull it in somewhere, right? So we're pulling down the air like this. So in that case, gravity is winning out. That make sense? So think of it in terms of which of these two forces is the stronger of the two. So in an area of low pressure, we know that we're overloading the middle of that low, so we've got to pull that air up. So we're going to fight against gravity, right? Because gravity's going to say, no, 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 no. That air doesn't go up. That air stays down at the ground here. It's like the bouncer at the club. Nobody gets in. You pay your $10. Okay? So what's happening is that the vertical pressure gradient force is overriding gravity, so to speak. Obviously, it's not going to just keep going into the sky. It has limits. But for the sake of argument here in theory, it's going to overload that. If we have an area of high pressure at the surface, we are increasing the air pressure, and if we're increasing the air pressure, we're smooshing it closer and closer to the ground. Well, what's the bigger, greater force when we get closer to the ground? Gravity, right. So that's the overloading force there. So when we talk about these areas of high and low pressure, this is kind of the two battles that are going on. And the equilibrium between the two, which is why if it was just a true equilibrium, one, we wouldn't have any weather at all because these air parcels would just remain suspended between these two forces. Clearly that's not the case because we have all kinds of stuff going on, so they are in constant battle with each other. Okay. So geostrophic, well actually I want to do, yeah, I'll do gradient. So gradient wind is basically the idea that what direction is the wind flowing to and from, okay? And don't get too locked in on all of this here because this will get way confusing. Just know that the idea is similar to what we learned earlier with these, is that gradient wind means in an area of high pressure, the pressure gradient force is weaker than what's happening with the Coriolis and the centripetal force in an area of high pressure, right? So winds in the area of high pressure, because the pressure is really high, right, and everything's getting smushed down close to this ground, to the surface, we got an overload here, so we have to do what? We have to move all that air out, right? So all of that's going to eventually move away from the center. Well, if we have too much in the center, it has to go somewhere. So it's going to move in the direction of that pressure gradient force. So all of that air is going to move towards the low. Because the low in particular is doing what? Trying to move air towards the center. So when we look on a surface map and we say what direction is the wind generally moving, it's going to be moving from areas of high pressure to low pressure. That's what this whole map basically tells you, okay? Now the forces between the two, pressure gradient force is stronger in an area of low pressure, so it's going to pull all that air in towards it, versus at an area of high pressure where the pressure gradient force isn't as strong towards the center. It's stronger moving away from it. That's kind of what I'm trying to show you here. All right. what friction can do sometimes is friction can create a little bit of movement between the two. So if we've got high up to the north or top, low to the south, we already know that the pressure gradient force is going to go what direction? Like that, right? So what friction can do is it can either slow down that process, okay, or it can create a little bit of curvature. So similar to what we're seeing in between the buildings, if you get downtown, you may get, probably the best way to put this is, if you notice that when you are walking somewhere, even on campus here, and you get in front of a building, the wind all of a sudden dies down, right? Well, because the buildings serve as a bit of a blocker. So then as soon as you keep walking and you get past that building, the wind picks up again because you've gotten past that. And in fact, it may actually be a little stronger just around the corner of the building because that building itself is creating a little bit of friction. And so instead of getting a straight line, so to speak, of wind moving from high to low, it may actually curve it just a bit. So friction can actually serve as a bit of a shift, gravitational pull as well. So the bottom line when we're talking about surface winds, the thing you always need to remember is they always go from high to low. Okay? And the tighter those lines are, the tighter those isobars are as they pack together, the stronger the winds are going to be. Now here's another interesting part too when we were talking about with, in particular, airplanes. The reason why it's so bumpy going up and landing is because of friction. What you're doing is you're crisscrossing all of these different isobars, so these different lines of pressure. And as you're crisscrossing all of these, you're running into all these little frictional issues and characteristics. So the wind, the closer you are to the surface, the higher the influence of friction, right? It could be trees, buildings, mountains, whatever, right? There's things down close to the ground that are causing you to kind of run into them. So it forces the wind in a bit of an off direction, meaning that this force, this friction, overloads this balance, right? So we know that pressure gradient force is going to do what? Try to move it towards an area of low pressure. Coriolis effect, that's going to try to deflect it a little further back down to the surface. But then as we go up in the atmosphere, look what happens. Friction gets a little less, our pressure gradient force gets a little stronger, and so our wind starts to level out. And then as we get higher up into the altitude, let's say up the jet stream, for example, there's a balance. Pressure gradient force is pulling out, Coriolis and gravity is pulling in. Friction is null and void, right? Because there's no mountains, buildings, trees 30,000 feet up. It's just sky. So what happens is we create a scenario where our wind is running parallel right with the isobar, with the line of pressure itself. And that's why airplanes fly way up here. Because the computer on the airplane set it at, and I'll just make this up, you set it at 1,000 millibars, okay? Just make it up. So what the airplane's computer does is when it's scanning through the sky, the altimeter is saying, I'm going to find 1,000 millibars. So when it finds 1,000 millibars, it just rides along that line, just like a track. Now what can happen sometimes is, and if you've ever been on a flight and they get on there and they go, we're going to run into a little disturbance, and they realize, they say, oh, okay, we're going to run into a little disturbance. That means they're running into a scenario where you've got maybe a storm system, big area of low pressure, or something like that. So instead of that 1,000 millibar line, let's make this 1,000. So instead of that line being nice and straight, which it normally is because there's no friction up there, if we're creating a scenario where we've got a lot of upward movement because of a big thunderstorm or whatnot, that 1,000-degree line, or that 1,000 millibar line may look more like this. Okay? So a little more of a wave. Well, normally we'd say, okay, well, who cares? That's no big deal. But think about if you're in an airplane and that airplane's job, that computer's job is find that 1,000 millibar line. And let's say it's here, and then let's say it's here. What's the plane going to do?
Go down.
Yeah. Plane does, it's not going to go, oh, I'll make everyone sick if I do this. It's just, its job is find that millibar line. So if it's here and it drops like that, sometimes that drop can be fairly drastic. It'll go just to find it, right? So that's why they have to be careful when they say we're getting into this. Now, obviously, it's not normally that drastic. If you're running into turbulence and the plane's starting to do some of this, that's why, because this line is more like this. Okay, so it's just creating a little ripple as it moves on through. I was on a flight years ago to the Dominican Republic, and there was a huge storm off the East Coast. And it wasn't anything they could avoid just because, those flights that go down into the Caribbean, they generally fly out over the Atlantic because they're trying to stay out of the main traffic lane between DC, Boston, New York, because there's just flights in and out and up and down the East Coast. So they'll fly out over the ocean and kind of just get out of the way. Problem is that there was a massive storm over there, and there's no way of avoiding it. And I fly once a month to Tucson, and I've flown for years, and that was the worst flight I've ever been on. I mean, that thing just, it was boom, just dropped. And there's nothing they could do because, it just, that's the way the computers are set up on these things now. But it was wild. It was a lot more like this than it was anything else, so. And it's amazing to see because airplanes have gotten so advanced that they can track these lines and they sort of know if they're going to run into some nasty weather, they'll change the line that they're running on, but it's not something where you go, okay, we're going to go to 1,000 and then now we're going to track at 996, and it doesn't immediately just go, wow, it just goes down. It'll just slowly work its way through so that you don't even know that it's happening, and they'll adjust all the time as they're up there. So, but that's the reason why they fly way up in the sky here is because friction doesn't have an effect, and so the wind or the airplane in this particular example pretty much flow right along with that. So here's another idea. You guys already know this because we learned it way back when. Air flowing in towards the low, air flowing away from the high, high to low. Cats and dogs getting along. Everybody likes it. Okay. So as we said on a surface map, this is what it's going to look like. The closer you are to the low, the lower the number. The closer you are to the higher the number. So if I were to take those H's and L's off of here, and I were to, put this on a map, and I were to say, draw me where the areas of high and low pressure are, you'd be able to do it. Because you just look and say, okay, let me start counting. I've got 1,004 here. I've got 1,038 here. Ah, that's a higher number. I'm guessing that's where the high is going to be. And notice between the high and the low here, this low in Idaho, this high in, what is that, Saskatchewan? Sure. Notice in between those two, look how tight those isobars are packed in as you look up top there, right? So where do you think the strongest wind is?
Or the
Right, exactly, where they're really scrunched in together. And that's the scenario I was talking about, that if you've got if you have water in a bigger pipe, bless you, if you have water in a big pipe like this, and you take the same amount of water, and you squeeze that into a pipe that's this size, what are you going to do to the speed of that water? Same amount of water, right? How does a shower work? Right?
Or like a funnel.
Or a funnel, right, same way. You're taking the same volume of water, but you're putting it into a much smaller space. And so you're going to increase the velocity as that fires out. And so wind works the same way. All right. Okay. Yeah, some of this. So, interesting thing about wind in particular is that what happens in the upper part of the atmosphere can affect what happens down at the surface. So we've already kind of talked about that, and that's the idea of the buggy that I was telling you, is that what's driving up above can move things down at the surface, okay? And this is the scenario that we've already discussed, that you guys know about, that at the surface, horizontal winds diverge from the center, but a vacuum isn't created because air descends to replace the air at the surface, right? And we already talked about that. So if I've got air moving away, an area of high pressure, I'm pulling it in from up top. And then the exact same thing happens, but just the opposite, in the area of low pressure, right? So if I have, oh my goodness, if I have the low pressure here, wind's all moving towards the center, we're overloading that center, we got to move it somewhere else. So like that. So that's the continuity of wind. Now, a couple of quick things, and we'll get out of here. Real quickly, measurement-wise, here's another important one, and people mess this up all the time. When you talk about wind direction, when I say, give me the direction what the winds are, it's always the direction it is coming from, okay? It's not the direction it's going to, it's the direction that that wind is coming from. So whenever you look at a wind vane or a wind sock, when it's pointed this way, that's the direction the wind is coming from, okay? Because if you think about it visually, think about that arrow is being pushed by something behind it, right? So what is that pushing and what direction is it pushing? That's the direction of the wind. Here's another easy way I always check it too. Let's say you're traveling out on the Katy Freeway, okay? Down on I-10 or even on 59. Doesn't matter. Look for the car dealerships because almost every single one of them has a big old American flag and it's flying high, right? Know what direction you're driving on that highway and see what direction that flag is pointing. There's your wind vane right there. I used to use it all the time when I was driving in, because I used to live out in Katy and have to drive down to the station. And it's Mac Hake, I think, is the big one out there. And
any Chevy or Ford dealership has the biggest.
right, they got that big old flag out there. And you can watch it sometimes, and it's just, I don't know, I do this because I'm a nerd, and this is what I do as I'm listening by NPR, is, you know, see what direction that wind is flowing. So do that this week when you're out driving around. Look at those flags and see what direction they're coming in from. I'm not going to tell you what direction because I want you to figure it out. Because you got to figure out what direction you're going and what direction that wind is coming from, okay? And then see how it changes by Thursday and Friday. Because it will. But those are the most common instruments that we use to measure these. And then if we get super fancy-dancy, we use things like anemometers. These can be handheld, aerovanes. So what these do, like this one in particular, this is a pretty, common looking anemometer. It's just got little cups. The wind gets in the cup, moves it, and this in particular doesn't necessarily measure direction, it measures speed. So like the little handheld anemometers, there's actually a cool one that you can use for your phone. I have it in my car somewhere. It has the little cup feature, and it plugs into your phone jack, and then you download an app, and it turns your phone into a handheld anemometer. I've used it out reporting before when we've been in big weather scenarios, and so you just hold your phone up, and it turns into a little anemometer. It's pretty cool. I had no idea they had that, but somebody showed it to me. So these are the different ways that we try to measure the wind as well. All of those reporting stations that they have across the country that we use for our daily weather observations here at the airports, all across the country, they all have wind anemometers. They're all attached to those stations as well. And that's how we get our wind direction, our wind speed, all of that good stuff. That's why during Hurricane Michael at Tyndall Air Force Base, which was right next to Mexico Beach, that took pretty much a direct hit, we were getting wind speed estimates as the storm was coming in. 120, I think the last one we got before the station was blown to pieces was like 145. So it went 145 and then it just dropped and went silent. We're like, well, there went that station. You know, and the buoys were doing the same thing. Most of those have little wind anemometers on them too. And we were getting readings, then the storm would come through and they just stopped working. Like, well, okay, that's destroyed. So, yeah, so they're really important information. It's something that we use on a daily basis, and very, very important, especially in terms of if you're going to be flying. You know, the big jets use it, obviously, but if it's a smaller jet, if you're in one of those little Pipers or those like two-seaters, you absolutely need to know what the winds are doing, not only at the surface, but as you get up as well, because you're going to run into some of that friction. So, yeah? All right. Everybody's like, whoa, man, it's Monday morning. Just filled my head with stuff. It's good stuff. All right. All right, guys.